So I have given your attendance link in the chat box. One of you can be in charge of that. So you can just copy and paste after maybe 1 or 2 minutes when other students also join the session. All right, I think we can start our lecture. So I will leave the chat box now. One of you can copy and paste the Google form in the chat box after maybe 1 or 2 minutes interval. Uh, so far we have established basic concept in tensors, and we have said that this tensor algebra or the classification of this tensor and all, it is relying on the transformation relation of that particular quantity in one coordinate system to another coordinate system. So, like for example, here in this case, Pj is a component of a velocity in one coordinate system that we call it unprimed, right? So this I have proved it unprimed. If it is in 2D system, then it is the XY system. And in this XY system, the coordinate variables are X and Y, or in this tensor notation, we write it as X1, Y1. Sorry, X1, X2. Now, this same quantity, the component of velocity means, suppose this is the velocity vector in one coordinate system, and P1 I cap plus P2 j cap. They are the two components of the velocity vector in unprimed coordinate system. Now, if you measure this same velocity in another coordinate system called prime coordinate system x prime y prime, here that quantity we let us denote it as p prime, and the component here in this case will be p prime 1 I cap, p prime 2 j cap. So they are the two components of the velocity in the prime coordinates. Now what we do is we try to obtain, or we obtain, in fact, in this previous calculation, we obtain the coordinate transformation between the components of velocity in the primed and the components of the velocity in the unprimed coordinate system. So the components of velocity in the unprimed coordinate system, we denote it as Pj. The components of velocity in the prime coordinate system, we denote it as Pi, Pi prime. So we write down the transformation relation between the components of that velocity, the physical quantity, in one coordinate system, and relates with another coordinate system using the transformation relation. So here we find that in the transformation between the components of velocity in one coordinate system to the components of velocity in the corresponding components of velocity in another coordinate system, the actual transformation coefficient is this. So this transformation coefficient, this partial derivatives here, involves the prime coordinate variable in the numerator, unprimed in the denominator. So if the transformation coefficients is a partial derivatives which involve the prime coordinate variable in numerator, unprimed in denominator, then we can conclude that that particular quantity is a contravariant tensor. And since there is only one index that is sufficient to represent the component of that vector, the velocity vector, then we can conclude that this is in fact what is called uh, contravariant tensor of rank 1. Contravariant tensor of rank 1. So actually that transformation relation is what we have discussed here. See, the velocity vectors. These are the components in unprimed. These are the components in prime. Then we write down the transformation relations. Here we see that the transformation relations are involving the direction cosines, and these direction cosines are like we discussed before. It can be replaced with these partial derivatives. These partial derivatives are equivalent to the direction cosines. I think I've discussed this. Partial derivatives are equivalent to direction cosines. Therefore, we see that the transformation relation between the components of velocity vectors, the transformation coefficient involves direction cosines or these partial derivatives. So they are same thing, direction cosines or partial derivatives, whatever you prefer. So this direction cosines or the partial derivatives is the transformation coefficient. And in this transformation coefficient, the prime coordinate variable is in numerator. Therefore, the physical quantity that is represented by this tensor algebra is called contravariant tensor. And since only one direction cosine is involved, also along with only one index is involved, then we say that this is what is that contravariant tensor of rank 1. Okay, contravariant tensor of rank 1. And also we discuss another system like this transformation of gradient of a scalar. And in this transformation of gradient of a scalar, here we write down these are the components of the gradient in prime coordinates, and these are the components of gradient in unprime coordinates. So here we see that components of the gradient in unprime, components of the gradient in prime, they are related by this transformation relation given by this. So in this transformation relation, the transformation coefficient is again partial derivative, but this partial derivative involves prime coordinate variable in denominator. Then this is called covariant tensor. When the prime coordinate variable and denominator, this is called covariant tensor. Okay, so these are something which you should keep in mind. So here in this case also, if we have covariant tensor involving two partial derivatives, see two partial derivatives as a transformation coefficient. If there are two partial derivatives as transformation coefficient, this is called covariant tensor of rank 2. See, in this covariant tensor, you see that in this transformation coefficient or the partial derivatives in this transformation coefficient, they are in denominator. Okay, so let's say we use K and L index, two index for representing this quantity in unprimed. Then the corresponding index for representing the same quantity in the prime coordinates. The same quantity is represented in the prime coordinates using two index I and J. Here in this case, I and K. So I, J, K, L. These are the two index in the unprimed, and these are the two index in the prime. So corresponding to I and K, we can write down the transformation coefficient. If we know that this quantity is a covariant tensor. Covariant tensor means that the index is represented in the subscript here. So in this case, K is the index for unprimed, so del xk is in numerator. I is the index for prime, so del xi prime is in the denominator. Therefore, this is the transformation coefficient for covariant. And similarly, j is the prime, means del xj prime is in the denominator of this partial derivative, and the corresponding index in the unprimed is L. Del XL is in the numerator. So like that, we can write down the transformation relation for covariant tensor of rank 2. Rank 2 in the sense there are two index here, K and L here, for representing that quantity the components of that physical quantity in one dimensional, that is, uh, unprimed coordinate system. So here in contravariant vectors, if we have contravariant vector of rank 2 means the two index here representing uh, the quantity in unprimed are k and l, right? KL. So KL, if you put it in the superscript, then that shows that this quantity is a contravariant tensor. This quantity is a contravariant tensor. So let's say we have ij as another the corresponding index in the prime coordinate variable. So they will have to be put in the superscript again to identify that this is a contravariant tensor. So I is the I j k l. So corresponding to k index, we have I index in the prime. Corresponding to L index, we have J index in the prime. So therefore, for this vector to be a contravariant, the direction cosines or the partial derivatives has to be such that the prime coordinate variable del xl, sorry, del xi, I is the prime coordinate variable, right? Next, del xi prime is in numerator, del xk is in denominator. So this shows that this is I and k are the contravariant index. I and k are the contravariant index because the prime coordinate variable is in the numerator and prime is in the denominator. And similarly, j and l are the contravariant index. So del xj prime, the prime coordinate variable is in the numerator. Del xl, the unprimed coordinate variable is in the denominator. So therefore we see that these quantities are indices for contravariant tensors. Now again, this is a very simple thing to show that velocity and acceleration are contravariant vectors. This, you see, in our unprimed system, unprimed coordinate system, even if we call x, y, z, then the coordinate variables are x, y, z system. So instead of x, y, z, we are going to use what is called x1, x2, x3, the unprimed system. And the position vector here in this case will be x1 I cap plus x2 j cap plus x3 k cap, right? So similar to that, the position vector in primed, in the prime coordinate system, position vector in the prime coordinate system will be r prime x1 prime I cap plus x2 prime j cap plus x3 prime k cap. So these are the position vectors. So you see that the component of position vector in unprimed is can be written as xj. Here you see that j index can go from 1 to 3 if you are having a Cartesian three-dimensional space. And position vector in primed, the components of position vector, position vector r prime in prime system here will be xi prime, where I runs from 1 to 3. So like we discussed in the previous lecture, when we write down the transformation relation here, I think I'll just show you where I did it. Yeah, here the position vectors. This is just a two-dimensional space. In a two-dimensional space, we have written down the transformation coefficient for the components of position vector, right? X and Y are components of position vector. See, if you are having two-dimensional space, xi, yj is position vector in unprimed. Position vector in the corresponding prime will be x prime I, y prime j. All right. So we have written down the transformation relations. And the transformation relations here involves the coefficient involves direction cosines. Cos theta are simply, theta is simply the angle between the two coordinate system, primed and unprimed. So if you recall that, uh, for such component of position vector, we eventually arrive at this. Component of position vectors, we eventually arrive at this. Here, when you arrive at this, you can see that by checking at this direction cosines here, by checking at the direction cosines or the partial derivatives here, you find that the coordinate variable corresponding to the prime system, xi prime, is in numerator, and this xj unprimed is in denominator. So that means position vector is a contravariant vector, because it follows contravariant vector transformation. Therefore, under the classification between contravariant and covariant vector, we can classify it as a contravariant vector because of this transformation coefficient or the partial derivatives, in which the prime coordinate variable is in numerator. Therefore, the following the tensor notation, the index here should be written in the superscript. Okay, so this is the correct way of writing the component of position vector. This is the correct way of writing component of the position vector, because they follow what is called transformation rule for contravariant vector. Yeah. Now, in order to get a velocity, we simply have to differentiate position vector. So when we differentiate the position vector with respect to time, you should keep in mind that, see, this coefficient, I don't think I need to turn back the page again. These stroke coefficients are actually cos theta, sine theta, and all, right? So theta is what? Theta is the angle between the two coordinate system, the prime system. This is theta, right? This is the y, this is the y prime. So this is theta. Theta is the angle between the prime and unprime coordinate system. So it is also independent of time. So when you differentiate on both sides, this is what you're going to get. Okay. So what is this? This is actually the velocity Vj in this is the velocity differentiation of position vector, means it will result in component of velocity in unprimed. This is component of velocity in prime coordinate system. So you see that this is component of velocity in prime. This will be component of velocity in prime coordinate system. Therefore, we can conclude that this is equal to this. That means the velocity in unprimed, component of velocity in unprimed, component of velocity in primed, they follow this transformation rule such that the transformation coefficient involves the prime coordinate variable in numerator, unprimed in denominator. Yeah. Now, in order to obtain the transformation equation for acceleration, we know that acceleration is differentiation of a velocity, right? So again, we differentiate with time, and also knowing the fact that this direction cosines, the partial derivatives for direction cosines, they are independent of time, dvj d upon t. So this is your component of acceleration in unprimed. This is component of acceleration in primed, a prime I. So a prime I will be equal to del x I prime upon del x j a j. So j is the index you use for representing component of acceleration in unprimed. So the corresponding coordinate variable is xj. I is the index used for representing component of acceleration in prime coordinate system, and the corresponding coordinate variable is xi prime. So in this direction cosines or the partial derivatives, the prime coordinate variable is still in the numerator and prime is in the denominator. So that means it still follows what is called transformation rule for contravariant tensor. Now, these are some examples of tensor of higher ranks. So actually, Albert Einstein has many higher order tensors like Ricci tensor and many names given, and there are some complicated tensors that was used in his formulation of general theory of relativity. So here we can have what is called mixed tensor. We can have what is called mixed tensor here. Just 1 minute. Here, mixed tensor means the component of a certain physical quantity measured in one coordinate system must have what is called it must have contravariant index as well as covariant index. See, if you put the index here in the superscript, this means that k is the contravariant index, and if you put L in the subscript here, L is the covariant index. L is the covariant index. So if the component of a certain physical quantity is represented using one covariant, another contravariant index, contravariant index together, this is called mixed tensor. If there are two indices here, that means this is a mixed tensor of second rank. Okay, tensor of rank 2. Now, here itself, you see that AKL, K is the contravariant index, L is the covariant index. So that shows that this is a tensor of mixed tensor of rank 2. Now, we can propose the corresponding quantity as measured in prime system. The corresponding quantity as measured in prime coordinate system as A prime ij. Here, I is the contravariant index, j is the covariant index. So what we have now is you have k and l in the unprimed, and you have what is called I and j in the primed. These are the index. You know that k and I are contravariant. If k and I are contravariant, then the corresponding transformation coefficient will be contravariant means del x I prime upon del x k. Here you see that L is the covariant index, J is the corresponding covariant index. So they are covariant index. L is the covariant index in unprime. J is the corresponding covariant index in the prime system. Covariant, right? So the transformation coefficient in this case will be for covariant. The prime's coordinate variable has to be in the denominator. So del xj prime del x L. Okay, so like this, you can write down the transformation coefficient. So this is exactly the transformation coefficient, but you have to, in order to write down the transformation coefficient, you have to identify which is the contravariant index, which is the corresponding contravariant index, and which is the covariant index, which is the corresponding covariant index. So by choosing such corresponding contravariant and covariant index respectively, you can write down the transformation coefficient. So you should know that for a contravariant index, the transformation coefficient should involve the prime coordinate variable in numerator and prime in denominator. And similarly for this this other thing like covariant index. In the covariant index, the transformation coefficient should involve the prime coordinate variable in denominator and prime in numerator. So they are reversed, right? Now, you can also write down the transformation relation for contravariant tensor of rank 3. So let's say you have a contravariant tensor of rank 3, it means the three indices are required to represent that tensor, and those three indices are written in the superscript. Those three indices are written in the superscript I, J, and K. And corresponding to this I, J, and K, let's say the corresponding contravariant indices in the prime system is alpha, beta, and gamma. Alpha, beta, and gamma. So here you identify that alpha and I, they are the corresponding contravariant index. So the transformation coefficient should involve del x alpha prime. X alpha prime, this is the prime coordinate variable is in numerator, del xj, the unprimed is in denominator. And here you can also identify that beta and j are the corresponding contravariant index. So del x beta prime, del xj, right? And similarly del x gamma prime, del xk. Here in all these three core transformation coefficients, since I, j, k, and alpha, beta, gamma are the contravariant indices, the prime coordinate variables are in numerator. Now, this is called mixed tensor of rank 2. Here you have two indices I and j for the contravariant index. Correspondingly, you have alpha and beta in the prime system, and k is the index for covariant. Uh, uh, k is the index for covariant index, right? And the corresponding character used for representing the covariant index in the prime system is gamma. So you can write down the transformation coefficient between alpha and I, and you can write down between beta and j, and also you can write down between gamma and k again. So if you write down between alpha and j, you know that alpha and I are the contravariant indices. So they have to follow this transformation coefficient such that the prime variable is in numerator. And similarly, beta and j will also follow. But here we see that k and gamma are the covariant indices. So the direction cosines or the transformation coefficient will involve partial derivatives such that the prime coordinate variable is in denominator. Prime coordinate variable is in denominator. Okay. And if you can identify like that, you can write down the transformation relation for this aijk also. Aijk. Here, alpha, beta, and gamma are again used for the corresponding indices in the prime coordinate system. So alpha and I are the contravariant indices. So the partial derivatives will involve del x alpha prime in numerator, del x I in denominator. However, beta and gamma, beta and j and k, beta and j, gamma and k, they are the covariant indices. So the partial derivatives will involve the prime variable del x beta prime in denominator, del x gamma prime in denominator. However, the unprimed del xz, del xk are in numerator. Okay. So similar to that, you can write down the transformation relation for covariant tensor of rank 3. IJK, covariant tensor of rank 3, IJK. And let's say the corresponding indices are alpha, beta, and gamma. Yeah, alpha and I are the corresponding covariant index. So if it is corresponding covariant index, the transformation coefficients for such index will be del x alpha prime in denominator, del xi in numerator. So you can write it down like that. Here you find that, see, In this same expression, I is a repeated index, j is also repeated, k is also repeated. That means there is a summation over I, j, and k according to Einstein's summation convention. And the indices that are repeated in the same expression are called dummy indices. Okay, they are the dummy indices. So I will stop here. I don't want to get too much into your head now. You go through all these things, go through the notes provided to you. So spend some time with the notes. Maybe we can continue next Tuesday. Okay, I will stop now. I don't want to feed too many information in one go. You go through the notes provided to you. Listen to my lecture once again. You work it out yourself. These are something which should be understood easily.